what exactly are you plotting here? So those are the constants.
This is the percentage. Okay, I see what the issue is. Time after the shock wave reflection. So the reaction begins at time 0, and the reactant, which is this methylformate, goes away. And the CO comes up. But I plotted it as the percent of the oxygen. So the idea is to see if I can track where all the oxygen atoms are.
Oh, I see.
So initially, all of the oxygen atoms are in the methylformate. So it's basically mole fraction of oxygen atoms, something like that. And so because, I'm not going to show it, but because we were able to track something like 95% of the oxygen, I feel like we've kind of tracked all the major species, and this gives you the information we need to do some kinetic analysis. Nobody's ever really had this before. So for shock tube experiment, this is quite unusual. So the idea is by having multiple species, you can begin to constrain what happens as a function of time to a level you can test, improve detailed reaction mechanisms. If I gave you only one of these things, there'd be other ways maybe to fit it. Or if I gave you only a characteristic time, it's not enough information. So the idea is to have multiple species sensing. And the reason I showed it is simply because infrared measurements have allowed us to do this. Of course, we've been working on this for years, but nonetheless. So the infrared gives us wide access to multiple species of interest in combustion.
Thank you.
Okay, so I'm sure you're getting a little tired. Spectroscopy, I think, wears you down. It's a little bit like trying to figure out your taxes or something. There's lots of rules. And I've been working on this a long time, so you tend to forget how long it took me to learn all this, because I never had a course. But in a way, this picture on the right symbolizes what a primary goal would be if you were interested in combustion chemistry and you said, I'd like to measure OH versus time or something. This is the sort of information that you had to start from scratch and identify the wavelength you're going to use. This is the kind of plot you would make. It's a plot of the line strengths versus wavelength. And right away, of course, somebody might have done this for you. So you'd look at this and you'd say, the best place to measure OH is where these line strengths are the biggest. It's here in the so-called Q branch. So we have a Q branch. So it would say, well, you better be working here around 308, 309 nanometers. But I'm going to show you over a period of a couple of days how you calculate this graph. In many cases, so if you didn't have it, you might have to calculate it. It may already be calculated for you, and you go in and you read the paper and you say, I'm going to work at this wavelength, and you're kind of done. Okay, so we're going to kind of progress through 6 things here in lecture 3, which has more to do with electronic spectra. We did microwave, which is rotation. We did infrared, which is vibration, rho vibrational. Now we're going to do a little bit of an electronic. And when it's electronic, you can have electronic change plus vibrational change plus rotational change, and it's sometimes called rho vibronic. Different words. So we're going to pay attention to these potential energy wells, which are part of when you do systems, that is types of spectra, rotational. We're going to do some analysis, which basically says, how do you look at rho vibronic spectra and learn about the molecule? You have to understand this in order to use spectroscopy, although in the end, all you're really going to do is pick the wavelength, measure the absorption, impose the cross-section, and you're kind of done. But this is the basic understanding that you would need if you're kind of having to do it all on your own. Okay, so when you have electronic transitions, you have multiple wells. Each well corresponds to a different electronic state. And you're going to learn about this symbol later. This is called the term symbol. It tells me this is the A state, the B state, the C state. You'll notice they go from A to B to C. They progress up alphabetically. And transitions between different electronic structures are given sometimes names. For example, all of the lines that correspond to this system is called the N2 first positive system. Just is. Somebody saw it, gave it a name, and it sticks. And the transitions between C and B are all called the second positive. So when you get into the electronic transitions, all of a sudden life gets a lot more complicated than the rho vibrational. So we're going to talk a little bit about these wells. We've already talked about the potential energy well for a diatomic. RE is the minimum, distance between the nuclei. This is the force, and so over here we call this the attractive side, because if you come in this way, it pulls the molecule down and goes faster and faster. Conservation of energy. So it has a minimum potential energy and maximum kinetic energy there, and it goes racing up this side till it finally reaches this limit of energy, and then it goes back out unless there's a collision. That's the potential energy well. And the shape of this and the position is telling you something about the molecule, the distribution of charges. So a measurement of this allows the physicists who deal with these things to learn about the structure, test their quantum mechanical theories of how to deal with these molecules. Now, in general, there's more than one. Here's a case where we would have the ground one. The ground one, that is the lowest energy one, is usually denoted by a capital X. The first one up is usually denoted by capital A. There's some rules on this we'll talk about later. But this is the place to define all the common notations. So the dissociation energy of the ground state is usually called DE. Let's see, DE double prime there, DE double prime. So that's the dissociation energy that you might look up in the Janov tables or in some tables. These are the vibrational levels. This distance, TE, is the distance between the minima. It's given the word capital T. T is usually the term energy, but here it's also used as the difference between the minima. There's the dissociation energy of the upper state, DE prime. This is the distance, this is the difference in energy. This is now the same molecule. This is like, say, nitrogen. If you pull nitrogen apart one way, that is, if you start with this structure and you pull it apart, here's the energy that that system has, the two atoms. If you pull this molecule apart, it has that much energy. Why? Because one of the atoms has more energy. One of its electrons is in a higher state. And this distance right here is that conservation of energy applies on this plot. So this A state will have a different value of RE. It'll have different, it's a completely different molecule, just because you've changed an electron. You've changed the molecule. So you think of it as a separate molecule. So usually X for the ground state, A for the first excited state. T is this energy separation here from the minima. Now, if you are, let's say it's fairly cold, all the molecules are right here. You can ask, how much energy does it take to get up here to dissociate this state? So in other words, if you send in more light than that, more energy, photons with more energy, it'd be above this level, and you'll probably have an absorption that leads to a dissociation. On the other hand, this distance right here is kind of the minimum energy that you can send in and see any effect. If the photon has this amount of energy, there's no place for it to absorb to. So these are like minimum and maximum kind of frequencies that you might see in the spectrum. And the reason we care about this is we're going to look at the spectrum and we're going to see if we can learn something about the dissociation energies. It's now well established what the dissociation energies are for most molecules. But gradually over time, this has gotten better and better. When I was a graduate student, there was two schools of thought. One was the dissociation energy of nitrogen was 7.5 electron volts. The other one was 9.7. Equally split. How can this be? Well, gradually over time, the spectroscopists figured out that it had to be the 9.7. So dissociation energy is the key thing. It goes into your statistical mechanics. It appears in thermodynamic tables. So it's, let's see, and Professor Pilling was saying, you need to know some thermochemistry in order to relate forward and reverse reactions. So if you have you need that for the equilibrium constant. So dissociation energies are key numbers. Now, it's helpful to think about the difference in the time scale of different events that take place as molecules are vibrating and undergoing collisions and transitions. The characteristic time for one rotation is of the order of 10 to the minus 10 seconds, about. The characteristic time for one vibration is of the order of 10 to the minus 13 seconds. So that tells you that it vibrates a lot in the time it takes to rotate around one time. What's the duration of a collision? Well, that's a little tricky, but two things are coming together and they finally get close enough they feel each other, and then maybe they go sailing by. What's the time over which molecule A feels molecule B? Roughly speaking, it might be of the order of 10 to the minus 12 seconds, yes?
How are these times estimated?
Well, you could calculate them, but right now I'm just kind of telling you what they are and trying to explain it.
Mr. Hanson, can you repeat that question?
Okay, thanks. So the question had to do with how do how do I know what these are? How do I calculate them? They're kind of based on, these are approximate numbers. They're just to give you a sense of the relative magnitudes. You can calculate the rotational one from the information I've already given you. You can calculate the, and same for the vibrations. So right now I just want to get across the fact that there are huge variations in time, and you'll frequently like to look at a problem and say, gee, that time is short compared to this time. So if you want to calculate an event, you can assume maybe that the other one is instantaneous. So let me go through this and then maybe try to come back to your question. So it takes about 10 to the minus 10 seconds to rotate. It takes about 10 to the minus 12 seconds for a collision. It takes about 10 to the minus 13 seconds for one vibrational cycle. That just says that spring is pretty constant. This vibrates a lot for one rotation. So when you do a dynamical calculation of maybe two things coming together, one's rotating and the other one's vibrating, and you want to simplify the problem, you can decide, is it frozen in motion or is it rotating like crazy? Do I have to worry about this or not? That's all it's for. Meanwhile, the electron, the time for an electron to move from one orbit to another is 10 to the minus 16 seconds. What do you see? What you see is that that time is shorter than everything else in this problem. So it's a good approximation when you're worried about an optical transition from one electronic state to another, absorption of a photon. It's a good approximation to say that the molecule hasn't moved during that time. And so we'll say that it's much more likely for a molecule to have a given spacing and angular position to be essentially frozen as it goes from one electronic state to the other. Useful. That leads to an important approximation. Emission, now this is an interesting one. Because this is an atom or a molecule, we have to follow the laws of quantum mechanics and statistics. So if you have an atom or molecule in a state from which it can emit, when does it emit? In the absence of any collisions, it's just sitting up here in an excited state. And there's an allowed transition. When does it emit? You can't say. It's a microscopic system. You can only apply statistics. And so we'll talk about what's called the lifetime. What is the average amount of time it spends before it emits? It's not deterministic, except through statistics. But these times are of the order of 10 to the minus 6 to 10 to the minus 8 seconds. So all of a sudden you see we have huge variations in times. And so when you're thinking about one, it now becomes easier to decide whether the other one is fast or slow. That's all this is for. It's not meant to be used to determine anything, except you're going to see now this takes so little time that when I'm thinking about this one, I can imagine that, or when I'm thinking about one of these things, I can imagine that this is fast. Let's come back to your question if you want a little bit later. Let's see. So this is expressed in what's called the Frank-Condon principle after two famous physicists, Frank and Condon. And it says that since this time is short, during the time of an electronic transition, which is what we're talking about now, vibration and rotation are frozen. They don't move. It happens like a snapshot. It's vibrating, it's rotating, but that transition occurs with a frozen molecule. And that turns out to simplify the calculations by the quantum mechanicists who calculate these things. That they don't have to worry about the change in positions when they calculate this probability. That's called the Frank-Condon principle, and I'll try to show you how it's used in a minute. So if we have an energy level here, a potential energy well here, and another one here, and let's say we're here in the bottom. Now, when you're in the bottom, where does it spend most of its time? In V equals 0, and now you have to kind of use a little bit of quantum mechanics. In V equals 0, you can show that the probability function for the time it spends in given positions, on average, it's mostly in the middle. By contrast, however, as soon as you go to V equals 1, 2, 3, it spends most of its time turning around. And for all of those, it spends more time on the ends than it spends in the middle. So when you're trying to think about transitions, you recognize, well, it spends more time on the end. So it's got to start here and go up. And it's got to go up to another end. It's got to link up with another place that's likely. And that means it happens frozen. So this is the Frank-Condon principle in action that we're going to talk about here. So these characteristic times are what I try to use to explain this Frank-Condon principle, which appears in the quantum mechanical calculations. So people will use the Frank-Condon approximation to calculate transition probabilities. Very complicated calculations. But they're simplified by this approximation that the molecular parameters of orientation in the ground and lower state and the upper state are the same. Otherwise, it's too complicated. So the vertical lines means you go from this internuclear spacing to the same. You don't change. It doesn't have time to vibrate. And you imagine that if you spend most of your time in the middle, you have to go vertically and you have to hook up with an end. This is a simplified interpretation of the Frank-Condon principle, which helps you understand the relative probability of absorption. So let's say you're here in the middle, V is 0, on average you're in the middle. You need to hook up with an end. And the most favored transition will be that for which it ends up with an end. So you could say, well, from here, there's one, and maybe if I use a longer or shorter wavelength, I won't be on an end, and it's going to be weaker. So it turns out that whereas there's very rigid selection rules for V and for J, the selection rule when you have electronic transitions is very fuzzy, and it's called the Frank-Condon factor. So you can go from one V to another V, or from the same V to yet another V, and they'll have different probabilities expressed in the Frank-Condon factor. And it turns out that if these wells are right on top of each other, notice how this one's wider than this one? If they're right on top of each other and they kind of have the same shape, then almost always you're favored to go from say V of 1 to V of 1. The others won't appear, and that's called the triangular nature of the matrix. I won't get into this. So the Frank-Condon principle just says you can simplify what's likely to happen in terms of this vertical line model as the main reason to explain the Frank-Condon factors, which have to be measured. And later you'll see the Frank-Condon factors. So the point is, for vibration and rotation, you have very specific selection rules. Delta V, delta. Frank-Condon factors, there's no rule other than this principle. That if you know enough about this diagram and this diagram, you can anticipate the relative probabilities of going from 0 to 1, 0 to 2, 0 to 3. It's a complication. Now, you can have different kinds of spectra. You can have, whether emission or absorption, you can have discrete spectra, or you can have continuous spectra. Here's the Frank-Condon principle. It basically just says that R is constant. So you kind of always go from one end to an end. So if I go from this end, so I go vertical, find this one. That wavelength will be absorbed. If I go from the middle to here, the middle, that wavelength will be absorbed. Now this is just changing electronic energy. Remember, superimposed on this is all the vibrational and all the rotational stuff. So it's basically, the principle is R is constant. And you spend most of your times at the ends. Therefore, the most probable place is the ends, except for the 0, which is the middle. So there are a lot of statistics that I've just kind of averaged over for you there. Here's the idea. Vibrationally excited molecules spend more time near the edges. So you're out on a vibration, and then it takes a little while to turn around and go back. You spend time on the ends. And you can imagine that the longer the fraction of the time you spend there, the more likely that your transition will take place from there. And then you got to go on a vertical line, so you got to end up with another. These are some distribution function information for how these things are calculated. But the bottom line is you spend most of your time on the ends, except for V equals 0, where you spend most of your time in the middle. Now, if you're in absorption and it's cold, all the transitions are going to come from V of 0. But you can go to different V primes. Which one will you favor? The ones that follow the Frank-Condon principle. If you're in emission, it's more complicated because you can come from any of the upper level V's. You've got a lot of more possibilities. The absorption is easier to understand. So, but we're going to look at the spectrum, and there's two kinds. There is the discrete kind and there's the continuum kind. You're going to see this now, I think. So if we do, let me take the next one here. Okay, so you're measuring the absorption spectrum. You're parked down here somewhere. Nothing is going to happen until you send in a frequency which is at least equal to nu zero. There's not enough energy. You can't get from here to anything. Strictly speaking, I think I should have drawn this one. Well, I'm trying to do two things at once here. You have to have enough energy to go from here to here. But this one actually favors 0 to 1 because of the center to the end and end to center. So, but the point is you have to have enough energy for absorption to take place. And once you have more than enough at delta, what's going to happen? It's going to be a continuum. It's going to look smooth. So if you record the absorption spectrum and it looks like this, you've just learned something about this diagram. If you can spot this place where it transitions, you've roughly determined the distance from the minimum to the dissociation limit. If you can spot nu zero, you've roughly determined the distance from here to here. So the absorption spectrum has a lot of information in there about energies, electronic energies. So there's the dissociation energy and there's the electronic energy that we care about. Now, the wells that I've drawn for you are called potential energy wells. It's also possible to have a curve that looks like this. That's called a purely repulsive state. And that happens because when these two atoms come together, they don't like each other. The spins aren't right. So they can either like each other and then they pull each other in, or they can dislike each other and they go apart. That just means it never forms a stable molecule. It doesn't want to live. But states like this exist, and they can absorb light. And so when they do, you get a continuous spectrum. So the absorption spectrum tells you a lot about the character of the upper state relative to the lower state. That's the main message. Absorption spectrum in the visible and UV contains information on the electronic structure. Whether it's the first place, the transition to continuum, always continuous, gradually you learn more and more about how do you characterize this state. Okay, back to the same example that's in my lab class. So here's the so-called first positive system of the nitrogen. So you take air, low pressure discharge, 2 torr, a couple of thousand volts, emission comes out, and between 570 and 610 nanometers, this is what you see. And the students identify these things. And the arrow denotes the notation. So I'm going from 6 to 2. This is emission from V prime of 6 to V double prime of 2, 7 to 3. All of them have delta V's of 4s. The Frank-Condon principle. It's the Frank-Condon principle saying it likes these. It likes delta V of 4s. If you looked out here, longer wavelength, there'd be the delta V of 3s and delta V of 2s and so on, and they wouldn't be as strong. So the Frank-Condon principle is just saying the alignment of the wells is such that it wants to go with a delta V of 4. 12 aligns with 8, 11, 7. So these are just general ideas I'm trying to get across to you. So you see the spectrum, you want to understand it. The signal, the interpretation would be that the height of this signal is proportional to the population in 12. Now, the height of this system is proportional to the population in 11, and you might say, why is there more population in 11? Well, that's when it gets complicated. That's when you have to think about actual values of these Frank-Condon factors. But in a relative sense, you can understand this. Okay, now I want to switch to something that's a little more specific, fortunately. I'm going to introduce what's called the four-track parabola for rotational analysis. This is a more complicated version of what we did for vibration. Okay, so that should say upper. The four-track parabola is when we look at the positions of all the lines and we plot them and we see curvature. The term energy is always the sum of the rotation, vibration, and electronic, which is therefore F plus G plus T. So for the upper state, the energy of the state, or level, is BJJ plus 1 omega. So this is the anharmonic oscillator expression for vibration. This is the rigid rotor expression for rotation, and that's the term energy. That's the sum of the energy in a specific electronic state, vibrational level, rotational level. Now, we're only going to analyze the behavior as a function of J, so all of this is just a number in a given band. And we do the same thing for the lower state, and that's a constant. So when I take the difference, which is where the wavelengths are, the difference between upper state and lower state, it now becomes a function only of the J's and the B's. Now, I should have had, yes, that's supposed to be B. That's the B upper. That should have been B prime, and that should be a B double prime. So, if you look at the difference, it's of this form, where it's convention to use M for minus J and M equals J plus 1 in the R branch. And so, bear with me. You can write position of all the lines on this diagram, which I hope is coming up next, as a function of this variable. And you can see that there's going to be a band head. It means it's going to turn around, and we can identify where that is, and we can find the band head, and we can relate all of this to the values of B. So let me look ahead and see if I got this showing this next. Yes, okay, good. I'm going to go backwards. So if I plot, this is frequency and wave numbers. And at each one of these positions, there's a line. It's a complicated pattern because I'm going to just see all these lines and you have to figure it out. But by analysis, you can figure out what value of J. So positive M corresponds to this P branch and this other, the R branch, and this is the P branch. So M is the common denominator, but it's plus and minus. These are positions of all the lines sorted by M or J, and this is a band head. That means there's no line to the right. So we learn something by the null gap, we learn something by the band head, and you're going to record the spectrum and you have to interpret it. And it's done this way. Now let me go backwards. So where's the band head? You can solve for this TDM in terms of this expression, and you can solve for it. And then using values for O2, you would see that it occurs at a value of M of only 3. So even when J is low, like 3, you can see a band head. Remember when I said for CO, where's the band head? Like 100? J of 100? Ah, for electronic states. It depends on the B's, and they're very different. The B's for oxygen are entirely different in these two states. So you can get a lot of band head action going on. So you measure this, and you can interpret it. You can fit it, and you can find, what are the parameters? A and B. The difference and the sum of the B's. That's all there is in this problem. So in a given band, in a given system, a given band, you do rotational analysis and you find B's. You do vibrational analysis to get the omega E's and the X's. And you can look at the structure of the spectrum to get at the TEs, the term energies and the dissociation. So all the information is in the spectrum, but the simplest one to deal with, because it's very quantitative, we just measure the positions. We're not using strings. The positions of the lines determine the values of B and B prime, B double prime and B prime. So by fitting this to a parabola, we get both A and B. So I'm going to give you an example. This might seem a little complicated. The steps that we have to go through to do this rotational analysis. I'm going to go through okay, let's see. Okay, let me go backwards. Okay. You're going to be given a section of spectrum. There's going to be like 20, 30 lines. You don't actually know anything except that they're part of one band. You want to interpret it to see if you can get B prime and B double prime. So first of all, you have to separate the spectrum into a band. Doesn't make any difference really what band it is. You got to separate it. You tabulate the positions, you identify the null gap, and you begin to label these lines. This is not trivial. But once you've done it, you can infer B prime and B double prime. You're done with that. What else do you need to know? Omega E and XE. What else do you need to know? TE. You're done. Those are the parameters that specify the spectrum. And we do rotational analysis. And so I'm going to illustrate this. If you use the expressions, I introduced what's called the first difference and the second difference, which are the differences between states and then the difference in the spacings. And again, this is in your notes, so I'm not going to dwell on it. So this is the homework problem I typically give in my class. This is a section of the absorption spectrum, probably the emission spectrum, for the A to X system of chlorine. So this is a real spectrum. 35 chlorine, that's the isotope. And this is the A to X system. And these are some of the lines in wave number units that were recorded and identified as being part of the 0, 0 band. How do they know it's the 0, 0 band? Well, maybe they would look and see, well, there's the 0, 0 and the 1, 0. You'd look at it and you'd figure out by energy which one is which. And then you say, these are the lines that I measured in my 0, 0 band. What do I want to know? I want to know BE, I want to know B prime and B double prime. That's all I can get from this. And it's a little tricky. So, because from the B's we can get the R's. So, what you do, typically, let's see how much information I've got on here. You go out to the end. That's the bandhead. These are frequency units. The bandhead is always out here. It can be either in the P branch or the R branch. If it's at the high frequency end, it's in the R branch. So that's the bandhead. So somewhere in here is the null gap. Somewhere in here is the information I need to get BE and BE double prime. How do I do that? Well, we can figure out that it's actually right here, and I'll show you how we do that. You start at the end, typically, at the other end, and you take the spacings. That would be the first difference. I said that right? I didn't say that right. That's the second difference. The spacing between, these are the wavelengths of the absorptions. The difference between these two units would be the so-called second difference. If it were a rigid rotor, that would be a constant. So we know it's almost a constant, and that's my clue. If I take the difference between these two, I get 1.88, the next one's 1.7, the next one's 1.53. Do you notice a pattern? Each one's declining by 0.017. That's the constant correction term. So you can be clever as a creative detective, and you work your way up through this. So the difference here is 0.18, 0.17. It's essentially nearly always 0.17. It'll just continue. Now, in order to maintain my 0.17, I now realize that this one has got to jump to this one. So I've just now encountered one of the lines coming down the other way. I'm going to go up this way, and then it's got to come back, because there's the bandhead. So you work at the extreme, work your way up, and you work on the principle of a constant second difference. So a constant correction. Call it T2. So you can do that, and now I haven't yet figured out which line I have. Except when I do this, I can figure out where the null gap is, and then I have to continue to decline by 0.17. Except once I reach the 0.14, it's got to turn over and go the other way. It takes some studying to do this. When you do this, you can figure out the identity of all these lines. That's called rotational analysis. It's not trivial, but it's exact. And from this, you can figure out the null gap value. You can figure out the value of 2A, which is T2. And now that's one way to do it. If you've identified the lines so that you know the J's, you also can use my other trick of common states. So what does common state mean? I find the transitions which both end in the same J. So let's pick J prime of 1. The two possibilities are P of 2 and R of 0. They both end up at the same place. If I take the energies of those two colors and take the difference, that's 6B. So I've just determined B. That would be B double prime. And you can do the same thing for upper states and lower states. So rotational analysis is all about finding B's. Why do I care? Yep. B tells me about the molecule. B tells me I need it in order to calculate the spectrum. So you either need it to calculate the spectrum or use the spectrum to calculate the B's. If your goal was to measure chlorine, you probably wouldn't go through all this problem. You'd just go to the database and use it. But you have to kind of go through this once. Appreciate it. Okay, that's rotational analysis. So in contrast with the Frank-Condon factors, which are very fuzzy, it's very specific. Record the spectrum, identify the lines, analyze the spectra, infer B prime and B double prime. You can do the, now what are the parameters for vibrations? Omega E and XE. Lower state, upper state. I could do that. How do I do that? So you can use either absorption or emission. The right frequencies are the same. And now this is called the De Landry's table. So before we use kind of four-track parabola, method of common states, rotational analysis. Now here you use something a little different. You use this so-called De Landry's table. The De Landry's table is the intersection between different values of B prime, double prime, B prime. So this entry here would be the null center gap, null center frequency from 0 to 0. What does null center mean? That's the one where there's no line. It's the missing line. So you have to find that, and there's one for each one of these bands. And you enter these numbers. So 0, 3 means I'm going from upper state 0 to lower state 3. And you put in some numbers. Then you go back to the, should have been G of V, to these harmonic oscillator, anharmonic oscillator expressions, and you take the differences. This is G1 minus G0. That should be right here. That's omega E minus 2 omega E XE. And so on. And so you can find the values of each of these things, but when you look at these, you see that these differ by 2 omega XE. So again, we recognize that with the anharmonic model, if we're harmonic, all of these numbers would be essentially the same or constants except multiple, except this would be double. But now I can look at these expressions and I can find out this energy difference is this omega E prime minus 2 omega E XE prime. This one is, and so this is the second difference. So they always shift by 2 omega E XE. And I can do the same thing on this direction. So when you go this way, you learn about B prime. You go this way, you learn about B double prime. I'm throwing a lot of stuff at you. This is something I spent a whole lecture on, say, at Stanford. So what do you need? You need the values that you come from your spectra. You take the spectra, you observe all of those null gap frequencies. You need several. You put them into the table. You write down these expressions if you need to, so that you can evaluate the first and second differences. See, the nice thing about this is that second difference is a constant. This is if you keep only one correction term for the harmonic and anharmonic oscillator. So here's some actual numbers. This must be, it looks like I'm not telling you what it's for. So what I do, first thing you do is you take this difference, take this difference, take this difference. 1480, 1460, 1420. You notice that they're all shifted by 20? Same thing down here. Take this difference, this difference, this difference by 20, by 20, by 40, by 40, 40. So immediately I only need like 6 or 7 entries in this table and I've determined everything. So here's the summary. You use rotational analysis to learn about the B's. D you hardly ever can get at. The B's and the alpha, these are the two main ones right here. Use vibrational analysis, De Landry's table, to get these. You can get it both for the upper state and the lower state. Use emission analysis to get at some of these dissociation energies. Okay, when you're in it, if you're doing absorption, you can end up in different upper states. So you learn about upper states. You learn about upper states and the dissociation energy of the upper state and the term energy of the upper state. If you're doing emission, you learn about the lower state. You always learn about where you're headed. So by combining emission and absorption, you can learn all of these terms. So we use rotational analysis here. We use De Landry's tables here. We use emission and absorption analysis to get at some of these D's and so on. Sometimes you get these transitions between continuum and structured, like this here. But remember, in emission, you're starting up here and you're learning about down here. In absorption, you're starting here and you're learning about up here. So there's always a way to get what you want. If you're doing combustion chemistry or combustion, the dissociation energy is really an important number. And I'm going to show you some ways that we can get at the dissociation energy. It's not kinetics anymore, it's thermochemistry. And for the longest time, we could never get closer than about 5%, 3 to 5% of what we calculated when we used the existing heat of formation of OH. And so finally we decided, is it possible that the heat of formation of OH is wrong? That's like saying the dissociation energy is wrong. And we studied this for about a year and then finally decided, we think it's wrong. You wouldn't think that the heat of formation of OH could possibly be wrong like this. But sure enough, we reported it at a meeting. At the same time, somebody named Rusik from Argonne reported his number. So it turns out that it was right. The GRI mech value and the JANF, the Sandia database values were just wrong. So what did we do? We used spectroscopy to measure the amount of OH. We measured our OH and compared it with a kinetic simulation in a regime where it's only dependent on the thermochemistry. And we found that they don't agree. So to get there, we had to figure out the quantitative absorption coefficient of OH to a couple percent. And then we used it to do thermochemistry. Okay, that's a lot of stuff. And so you've got my notes. I apologize. A lot of those news in there should be V's. But other than that, I think they're pretty good. And you know, what I'm trying to do is, I just want you to see A, how powerful is spectroscopy. It is complicated, but we do it, it's powerful. So you just want to get a flavor of this, unless you're already working on this for your research. Any questions? So we're talking about UV, we're talking about visible, infrared, rotations, vibrations, electronic, it's all kind of the same. Positions of lines, strengths of lines, shapes of lines. Today we're really mostly focusing on positions, a little bit on the use. This last example made use of the strength. This is actually the simple presentation. You're going to see how the notation gets more complicated fast. But you know, these spectroscopists, this is their life. This is all they do. We're more interested in applications. But we have to understand it. We accept quantum mechanics. You don't have to even do a quantum mechanics calculation. Just accept it. Use it. Okay? Thanks for your patience today. See you tomorrow.